Hi everyone, welcome to a short tutorial lecture on encoding. Okay, so you should have watched the lecture on encoding first, and what I'm going to do in this tutorial is I'm just going to solve some problems like you would see that have to do with encoding. Okay, well actually before we did the encoding we kind of finished off with Moore's law, so let's do a couple of questions with that first, and then we can move on to the encoding questions. Okay, so the first question I have here is how many transistors does it take to make a full adder which is 32 bits wide? Okay, so remember what it means to say something is 32 bits wide. It means it has 32 columns. Okay, so 32 bits means that you have 32 columns, and that means that you have 32 3-bit adders, because in order to make a full adder, each column in your full adder is a 3-bit adder. Okay, now if you go back to the lecture, you'll see that to make a 3-bit adder, it takes 17 transistors. Okay, and so you basically have 32 times 17 transistors. Okay, because you have 32 columns. Each column requires 17 transistors for a total of 544 transistors. Okay, so in very old computers, like about 20 years old now, you would have they were 32-bit machines, and that means that the adder inside the central processing unit was only 32 bits wide. Okay, and older phones, not that many years ago, but most phones a few years ago were 32-bit phones as well, and so their adders would have had 544 transistors in them. Okay. Easy question to start with. Here's a second question, okay, and this is based off of Moore's law. I paid $1,200 for a computer 3 years ago. How much would it sell for on eBay today? Okay, and I've actually looked at this. I've looked at how much computers sell for on eBay, and they follow Moore's law pretty precisely. Okay, so how long has it been? Well, I sit here 3 years, and remember that Moore's law says that computers double in computing power every 1.5 years. Okay, and that means that they reduce in price to 1/2 the price in 1.5 years. Okay, so in 3 years you've basically got 2 cycles of Moore's law happening. Okay, in other words, the computer will depreciate in price to 1/2 of its original price, and then it'll do it again for the second cycle. Okay, and so that means that in all it's going to be 1/4 of the original price, because it's half of a half, which is a quarter, and a quarter of $1,200 is $300. Okay, so this computer that I paid $1,200 for 3 years ago is only going to be worth $300 today. Okay, and that answers the question, but I just made a little chart here to show you how that depreciation goes. You start off with $1,200 like now. Okay, in a year and a half that reduces to half that price, which is $600, and then in another year and a half, for a total of 3 years, it reduces to 1/2 again, which is $300. Okay, so you can see how quickly you depreciated. That's a depreciation of $900, almost $1,000 in 3 years. Okay, now I should also add that computers are they'll last a very long time. Okay, but what winds up happening is that it's not that they're slowing down inside, but the software that you want to run will often be demand more computing power, and so older computers are sometimes annoying because they seem slow. Again, it's not that the machinery inside is slowed down, it's that the software that you put on top of them demands more computing power, because the software is made for a modern computer, and so that's why they seem to run slower. Okay. All right, so the next question, so those 2 questions were about hardware and Moore's law. The next question is our first question to do with encoding. Okay, and so I ask a question here. Old Sumerian, which is an early Bronze Age language from about 3000 BC. Okay, was written with about 1,000 different cuneiform characters. I'll show you a picture of cuneiform in just a second. Okay, what size encoding would you need to encode Old Sumerian text? All right, so basically you have 1,000 different characters, and I'm asking you how many bits would you need per character in order to encode 1,000 bits? Okay, and then part B is late Sumerian. Okay, this is from the late Bronze Age, about 1000 BC. Reduce the number to about 400 characters. Okay, so you went from 1,000 characters down to 400 characters. What size encoding would you need to encode late Sumerian? Okay, just if you're curious, this is what Sumerian looks like. Whoops, let me bring up. There we go. So you might have seen this before. They're like a little wedge little wedge drawings. Okay, and here's a picture up close. This is old Sumerian. It's a little bit like hieroglyphics, but not quite. Okay, it was made with like a flat stick. Okay, looked almost like a screwdriver. And this is later Sumerian. You could see that it's much more stylized. Anyhow, that's just an aside, a curiosity. Okay, it doesn't have any bearing on the answer. Okay, but it's kind of like Chinese with logograms. Okay, and so let's do the first one. So if you need to encode 1,000 characters, how many bits would you need? Well, just remember that chart that I gave you. Okay, if you have n bits, all right. So if you have n bits in your encoding, you can encode 2 to the n data items. Okay, so n is just any number you like. So say it's 5. So if your encoding has 5 bits in it, then you can encode 2 to the 5 data items. And 2 to the 5 is like 2 times itself 5 times. Okay. Now, I kind of wrote down some numbers here. If you have 8-bit encoding, then you can encode 2 to the 8, which is 256 items. We saw that with extended ASCII. If you have 9 bits, you can encode 512 items. And if you have 10 bits, you can encode 1024 items. Okay. Now, you can't quite do it with 9 bits, Old Sumerian, because you need 1,000 characters to do that. Okay, and 9 bits will only give you 512, and that's not enough entries in your encoding to make it to 1,000. Okay, but if you get to 10, then that is sufficient. Okay, and so for Old Sumerian, you would need 10-bit encoding. Okay, again, 9 bits is not enough because it only gives you 512, and 10 bits is enough. Okay, so you want to get the smallest number of bits possible, but as long as it's enough to cover all of them. Okay, and you say, well, why not 9.5? Except that what does half a bit mean? Okay, so there's no such thing as a fraction of a bit. Okay, now late Sumerian, you only have 400 characters, and you say, well, 8 is not enough. 8 bits is not enough because you need to get to 400, and 8 bits will only give you 256 entries in your encoding. And if you go to 9 bits, 9 bits will get you to 512. Okay, and that is enough because that's greater than 400. Okay, so you want to go bigger than your lower number and less than your upper number. Okay, and so for late Sumerian, 9-bit encoding would be enough. Okay, 8 bits again is not enough because that only gives you 256 and you need 400. 9 bits gives you 512, and that is enough because you need to cover 400 data items. Okay, so there you go. There's an example of, if you were to make this encoding from scratch and you wanted to encode only Sumerian, that's the number of bits you would need. Okay, and just as an aside, Sumerian is, even though it's an ancient and an extinct language, it is in Unicode, so you don't have to re-encode it. But if you wanted to encode just Sumerian, you could do it with Old Sumerian. You would do it with 10 bits, and New Sumerian you would do it with 9. Okay, let's move on to the next question. Okay, so the following line is in ASCII. Okay, and how many bytes are required to encode the entire line? Okay, now remember with ASCII, extended ASCII, so if I don't say extended, just assume I mean if I just say ASCII, assume I mean extended ASCII, because that's the only ASCII that we use today. Okay, the older ASCII is not used anymore. All right, and that means 1 byte per character. Okay, so all you have to do to answer this question is count the number of characters in that sentence, and that's how many bytes you would need. Okay, so let's do that. Okay, so the sentence is, it's raining in Spain, like that. And so we can count, and we have to count everything, not just the letters. We have to count spaces. Whoops, like that. Okay, we have to count spaces. We have to count apostrophes. We have to count, exclamation points. Everything that is part of the writing system. Okay, even the white space characters. Okay, so let's go through here. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. Okay, and so there are 24 characters, including the 3 exclamation points. Okay, each exclamation point is going to be another 1 byte. Okay, and so there are 24 characters in all, including the spaces, apostrophe, and exclamation point. And so 1 byte per character. So, whoops, I didn't say it here. So the line requires 24 bytes to encode. Okay, there you go. That answers that question. So ASCII was really nice because, again, all you had to do was just count the number of characters. It gets a little bit more complicated with other types of encodings. So the next question is a Unicode encoding, and I said, okay, the following line is in Unicode. How many bytes does it require? Okay, so Unicode is 4 bytes per character. Okay, so every single character is 4 bytes. Even if it looked like ASCII, like, you could have this sentence right here. Okay, and that sentence, it can be encoded in ASCII because it's just plain old English. But you could also encode that same sentence in Unicode. Okay, anything that's encoded in Unicode, every character is 4 bytes. Okay, and so here I've got 6 Chinese characters and 3 exclamation points, and so it's basically 9 characters, 9 Unicode characters. Let's count them. Okay, there's 1, there's 2, there's 3, there's 4, there's 5, there's 6. So there are 6 Chinese characters, and then 1, 2, 3 exclamation points. And even though these exclamation points look the same as these exclamation points here, okay, these ones are Unicode exclamation points, and so even they require 4 bytes. Okay, and so again, 6 Chinese characters and 3 exclamation points for a total of 9 Unicode characters. Okay, now 9 Unicode characters, each Unicode character is 4 bytes, and that'll give you 9 times 4 or 36 bytes. Okay, so that entire line requires 36 bytes of text. Of information. Okay, so 36 bytes to encode that text. Now I asked the question, how many bits is that? Because I want you to also know the difference between a byte and a bit. And a byte is 8 bits. Okay, so it takes 36 bytes to encode that line, and each byte is 8 bits. And so if you multiply 36 times 8, it gives you 288 bits. Okay, and a bit is a binary digit. So if you could look inside the computer wherever this information is encoded, okay, like the mere fact, you might say, well, what do you even mean, like inside the computer? The mere fact that that's appearing on my screen, or it's appearing to you through YouTube, and it's appearing on your screen or whatever, means that somewhere inside there had to have been some kind of encoding going on. Okay, and wherever that is inside the computer, not to get into the details of all the details of the internals of computers, wherever that is, it's basically encoded with a sequence of 288 ones and zeros. Okay, and whenever the computer encounters those 288 particular ones and zeros, it says, oh, you want me to draw that text there. Okay, and that's what encoding is. All right, okay, so 36 bytes or 288 bits. Okay, let's do question number 6. Estimate the size of a file which contains 1 page of ASCII text. Okay, now this is an estimate question. We're going to do a lot of these in a future video. Okay, so we're going to do a lot more word problems than the ones that I'm just doing right now. But whenever I say estimate, it means that it doesn't have to be perfect, but it should be in the right ballpark. Okay, like if you estimate that something is like 1,000 and the real answer is 1,000,000, that's really off. But if you estimate 1,000 and the real answer is 1,500, that's kind of close. Okay, you'll know that you're off because you'll be like totally wrong metric prefix or whatever. Okay, it'll become clear what we mean by estimate. All right, so if you're wondering like exactly how do you estimate, well, don't worry about that too much. Okay, right now it'll become clear as we go on. All right, so it says estimate the size of a file. Okay, so we have a file in our computer, and this file contains just 1 page of ASCII text. Okay, by the way, a program that works in ASCII in Windows is Notepad. Okay, and I don't remember what it's called in a Mac OS X, but I think it's just called text editor. Okay, and those programs, they're not word processors, which we'll study later. They don't do all sorts of fancy letters. They just do plain letters. In fact, the text that you're seeing here, this whole text right here, the way I teach these things with like my background there, that whole background, it's just plain old ASCII. Well, actually no, it's got Unicode in it. Okay, I shouldn't say that because you get the Chinese there. Okay, but most of it looks like ASCII, but it is actually Unicode. Okay, anyhow, let me answer the question. So usually when you say 1 page, and this is where the estimation comes in, you usually mean 250 words. Okay, and you say, well, where did you get that? That's the usual definition. If someone says write a 40-page paper, Okay, and you ask, well, what do you mean by a page? Usually what you mean is 250 words. Okay, could be a little more, could be a little less, but 250. Okay, now here's another estimation. One word, how big is a word, an English word? Most English words are about 5 letters long on average. Of course, you've got really, really long letter words, and you've got really short words like like a tree or something, or just one letter. Okay, but on average, it's roughly 5 letters. Okay, but then you have to separate the words from one another, and so there's usually 5 letters followed by a white space character, or maybe punctuation or something like that. Okay, again, this is an estimate. So basically, yeah, even though a word is 5 letters, we're going to say 6 characters because you need that separator from the rest of the words. Okay, so we'll say 6 characters, and a character, remember, if we're talking ASCII, is 1 byte. Okay, so there's all the information we need, and now we could say, okay, one page is basically 250 characters, and multiply that by 6 bytes. Why 6 bytes? Because each word is 6 characters long, and 6 characters is 6 bytes. So if you multiply 250 times 6 bytes, you get 1,500 bytes, or 1.5 kilobytes. Okay, 1.5 kilobytes. Now, how I converted from 1,500 bytes to 1.5 kilobytes, you'll see in some of the following questions. Okay, but basically, in when you're doing the assignment or you're doing the test, what I expect you to do is take whatever answer you get and convert it to an appropriate size metric prefix. Okay, now what does appropriate size mean? Okay, so 1,500, you can actually make that number smaller, okay, and bump up your metric prefix by 1. Okay, so what do I mean by that? Well, okay, each of the metric prefixes, to go from one metric prefix to the next, is like dividing by 1,000. Okay, and that's because if you go from bytes to kilobytes, it's 1,000. So 1 kilobyte is 1,000 bytes. To go from kilobytes to megabytes, it takes 1,000 kilobytes to make a megabyte. Okay, to go from megabytes to gigabyte, it takes 1,000 megabytes to make a gigabyte. Okay, and then to go to gigabyte to terabyte, 1,000 gigabytes makes a terabyte, and 1,000 terabytes makes a petabyte. Okay, and so each of the metric prefixes differ from the other one by a factor of 1,000. Okay, so you'll see more of this as I do problems in the future, but right now you see that 1,500, you go, well, I can make that number smaller. How? By dividing by 1,000 and bumping to the next metric prefix. Well, there is no metric prefix right here. It's just a plain old byte. So if you divide this number by 1,000, you get 1.5, and then you go from no metric prefix to your first metric prefix, which is kilo. Okay, so if you have 1,500 bytes, divide that by 1,000, 1.5 kilobytes. The word, that K there, you can even read it as 1,000. Okay, because that's really what it means. All right, so here on this side we would say 1,500 bytes. Here we would say 1.5 thousand bytes, and 1.5 is 1,500 bytes. Okay, so like how would you, like, how do you know how far to go? Because you could say, well, could I divide by 1,000 again? Yeah, basically the rule is something like this to get your appropriate metric prefix. It's the biggest possible metric prefix, okay, such that the number is still greater than 1. Okay, so we started with 1,500 bytes. Okay, if you divide by 1,000, you get to 1.5 kilobytes. Okay, and that's okay because you're still at 1.5, which is bigger than 1. If you were to divide by 1,000 again, okay, you would get 0.0015 megabytes. Okay, and that's too much because now your number is less than 1. Basically, you want to just take a big number, because you're going to see that our numbers get really, really big with these problems, and you want to divide by 1,000 and bump the metric prefix. Go to the next one up, in other words, and then divide by 1,000 again and bump the metric prefix. So you want to keep doing that until your number is bigger than 1 but less than 1,000. Basically, that's the way to do this. Okay. All right. So here's an example. Like you have 1,500 bytes, like in this problem. Okay. If you divide by 1,000, you get to 1.5 kilobytes. Okay. If you divide by 1,000 again, which you can do, you divide the number by 1,000, but then you bump the metric prefix from kilo to mega. You could divide by 1,000 again if you want. All right. So there's the number divided by 1,000 again, and then you bump from mega to giga. Okay, and you can do it again, divide by 1,000 again, and then you bump from giga to the next bigger one, which is tera. and so on. Okay, and you look at this and you go, well, this number has too many zeros on the right hand side. Okay, and these numbers have too many zeros on the left hand side, and so which one is the nicest number to work with? I think it's pretty obvious that it's that one. Okay, so I'm introducing this idea now, but in future videos when we look at more deeper problems with data sizes and data rates, okay, this issue will come up again. So you're seeing it for the first time now. Okay, so all right, let's do another problem here. Okay, so this has to do with pictures, okay, images, and again, it's one of these estimate. Okay, estimate the size of a bitmap, which is 450 by 300 pixels. Okay, so what that means is that it's 400 columns of pixels, because remember the pixels form kind of a grid. Okay, a pixel is a square, and it's a square which is all one color, and it's very, very small inside of an image, so you can't see it, and it kind of, your eye blurs it in with its neighboring pixels. Okay, and so if you were to look at this bitmap, you would see that it has 450 columns of pixels and has 300 rows of pixels, forming a grid. Okay, and how big is that? So estimate the size and express your answer with the appropriate metric prefix. Okay, I won't always say that, but I want to emphasize it now, that I want you to take the answer and just decide how much which metric prefix gives you a number which is bigger than 1 and less than 1,000. Okay, so there's that. And the last thing is, when I say estimate the size, I mean, one, there's the estimation, but you say, well, what do you mean by the size? I don't mean like you could say the size of an image. It's like, how many inches by how many inches. That's not what I mean by size, and that's not what we mean by size when we're talking about computers. By size, we really mean how much information, and the answer would be in bytes. Okay, so whenever you hear the word estimate the size, I expect the answer to be in bytes with a metric prefix, but in bytes. Okay, so let's do that. First, you do 450 times 300, because you've got 450 columns of pixels with 300 rows of pixels, and that tells you that the image is made up of, let me put some commas in there so it's easy to see, 135,000 pixels. Okay, so if you looked and you actually counted all the little tiny pixels, all those little squares, you would see that there's 1,350 of them. Okay, now remember, this is an image which human beings are supposed to be able to see, and for humanly perceivable color you need 3 bytes. Okay, so you need 3 bytes for every single pixel. So every pixel is actually 3 bytes long. Just like with Unicode, every character was 4 bytes. With images, every pixel is 3 bytes. Okay, so great, we have that each pixel is 3 bytes, and we have how many pixels there are. So just take the number of pixels and multiply it by 3, and that's going to tell you how many bytes. Okay, and I just put a comma in there so that it's easy to see. Okay, so this file, the size of this file would be 405,000 bytes. Okay, now 405,000, that's a big number. It's got too many zeros on the right, so divide by 1,000 and bump the metric prefix up 1. Okay, we just did that in the previous problem. So here, if you divide by 1,000, you just lose those 3 zeros there, and you get 450, like that. And when you bump the metric prefix, well, here there is no metric prefix, so you go to the first metric prefix, which is kilo. Okay, and you know what? You can read both of those exactly the same. Like this one, you could say 450,000 bytes, but if you read kilo as 1,000, this also reads 450,000 bytes. Okay, usually we would say 450 kilobytes, but kilo and 1,000 are synonymous. Okay, so I hope that helps to make sure you understand what these metric prefixes mean. Okay, maybe I should just write it here just as a reminder. K is 1,000. So if you have a kilobyte, that's like saying 1,000 byte. M is a million. So if you have a megabyte, that's like saying a million bytes. So if I say this file is 5 megabytes in size, that's exactly the same as saying it's 5 million bytes in size. And the next one is giga, which is billion. So you say this file is 4 gigabytes in size. That's like saying it's 4 billion bytes. Okay, and tera is trillion, and there is peta, but I don't know what the word is for that, because that gets to be a number which is bigger than we usually have a word for. Okay, all right. That's question number 7. Here's question number 8. It's another encoding question having to do with the encoding of colors. And now dogs have, people sometimes say dogs are colorblind. They're not exactly colorblind. They have two different cones, okay, and they see different colors than we do, okay. But we have three cones and they have two cones, so they have two primary colors and we have three primary colors, okay. Now, dogs have only two different types of cones, and approximate how many different colors a dog can see, okay. And I guess I could call that part A. And part B is bees have four different types of cones. Approximate how many different types of colors a bee can see. Okay, and compare this to how many colors a human can see. Okay, so let's do the dog first, part A here. All right, so part A, two colors. Each color is each cone is its own channel, a color channel. Okay, and so I don't know what the colors are that a dog sees, but whatever the one color channel is, it needs eight bits. Okay, so to encode a particular color channel, it takes 8 bits, and the other color channel also needs 8 bits. So two color channels each require 8 bits for a total of 16 bits. Okay, so to encode a color for a dog, you pick any particular color that a dog can distinguish from other colors. Okay, and it takes a sequence of 16 ones and zeros, 16 bits to do that. Okay, and so you say, okay, well, with 16 bits, how much can I encode? And remember that chart I gave you earlier. If you have 16-bit encoding, then you can encode 2 to the 16 colors. And if you just work that out on your calculator, that turns out to be 65,536. Okay, this really is an estimate because who knows? Like some dogs might see more, some might see less. It probably changes with age too. Okay, because our eyesight gets worse with age. Okay, so I would just say that dogs can roughly see 65,000 colors. Okay, now humans, we have 3 color channels. This is what I did in the lecture, but just to remind you, we have 3 color channels. So that means we have 3 primary colors. All the colors we see are made up of a mixture of these 3 primary colors: red, green, and blue. Okay, and each one of those primary colors has a different level associated with it. In other words, you can have a lot of red or very little red or medium amount of red. So there's like roughly 200 levels, which we encode with 8 bits. So the level of red is encoded by 8 bits, the level of green is encoded by 8 bits, and the level of blue is encoded by 8 bits, for a total of 8 plus 8 plus 8, or 24 bits. Okay, so to encode any human color, humanly visible color, okay, we need 24 bits. And then I can ask the question, how many data items can you encode with 24 bits? And if you have 24 bits, you can encode 2 to the 24, and that turns out to be 60,777,216 colors. Okay, again, same thing with a dog, and that's an approximation. Let's just say it's roughly 16 million colors. Okay, so that's how many different colors humans can see. When I say different colors, it means like if you got one color and another color and you put them together, if they're different colors, humans should be able to see the difference between the two. But if they're very, very close to one another, they might be too close. And even though they're different, like say there might be some experiment to show that these are actually different colors, they might be so close that humans can't tell the difference. So a better way to put this is how many humanly distinguishable colors are there? 16 million. Okay, dogs can distinguish 65,000 different colors. Humans can distinguish 16 million different colors. So it's quite a lot more. So we have a much richer color field than dogs do. And bees will just bees totally blow us out of the water because they have 4 color channels, including colors in the ultraviolet, which is beyond what we can see as human beings. Okay, and each one of those color channels is 8 bits. Okay, and so that's a total of 32 bits. All right, and you might ask the question, how many different colors can you encode with 32 bits? And the answer is that right there. So 2 to the 32 is that number there. That number is, I put commas in so you could see, it's 4,294,290. Well, I said it wrong. Hold on. 4,294,967,296. Okay, roughly 4 billion. Okay, so bees can see 4 billion colors. Okay, so again, dogs 65,000. roughly, humans 16 million roughly, and bees 4 billion different colors. Okay, so the kind of richness of the colors that that bees can see far exceeds humans. Okay, and we far exceed dogs. I can't imagine what a bee's world looks like. Okay, we can't imagine colors like that because their brains aren't wired to perceive that many colors, but apparently bees can. Okay, so if bees could talk, they would pity us. They would say, these poor humans, they can't possibly appreciate the richness of the color of flowers. Okay. All right, last question. And this question is, a library is made up of 65,000 books. Each book on average is 300 pages long. Okay, estimate how much information is in this library if the books are encoded in ASCII or if the books are encoded in PDF. Okay, so let's read the question again. So you got a library. Number of books in the library is 65,000. Okay, some books are bigger than others. Okay, some books are like 1,000 pages long. Some books are only 100 pages long. On average, a book is 300 pages long. Okay, and we're going to pretend for part A that all the books have been encoded in ASCII. Okay, which is kind of boring because it's just letters. There's no pictures, no fancy letters, no mathematical symbols, nothing, just English letters. Okay, just English text. Okay, and how much information is in that library? Okay, and now part B is do the same, but now pretend that the whole library, the books are encoded using PDF. Okay, so they're encoded as PDF. Okay, actually we don't say using PDF, we usually say as PDF, like that. Okay, and so how big would that library be? Okay, well, let's do part A first. So let's first calculate the number of pages in the library. So there's 65,000 books, and each book has 300 pages. So that's a total of, okay, let me put some commas in here so we can see how many. That's like 19,500,000 pages. Okay. Now each page is about 1.5 kilobytes. We just worked that out earlier. Okay. So each page is about 1.5 kilobytes, and so if you take the total number of pages and each page is 1.5 kilobytes, you multiply that out and you get this number here like that. Okay. Let me put some commas in there again, and so you get 29 million 250,000 kilobytes in size. Okay, now that number has too many digits to the right. Okay, remember we want the number to be between 1 and 1,000, and you go, okay, let's work that out. So if you take that number and you divide by 1,000. Okay, so take the 29 million, divide by 1,000. Well, if you do, basically these three zeros here just get lopped off and you get 29,250. But you have to compensate for that because now you got to go from kilobytes, which is the smaller, okay, of the two metric prefixes, to megabyte, which is the bigger of the two. Okay, so once again, divide by 1,000 and bump from kilo to mega. Okay, you can think of it something like this. You see that the 1,000 there? You take 1,000, which is in the number, and 1,000, which a kilo is, and 1,000 times 1,000 is a million, and that's what gives you that mega there. Okay, I don't know. I mean, whatever works for you to get your head around what's going on here. Okay, but this number is still too big, because remember, we want to be between 1 and 1,000. You say, well, what do I do? Divide by 1,000 again and bump the number up one more time. And so over here, you're going to divide this number by 1,000. And so now you're going to get 29.25. And you're going to bump from giga to the next bigger unit, metric prefix, and that's giga. Okay. And so basically, we had to do this twice. We divided by 1,000 and bumped the metric prefix once from kilo to mega, and then we divided by 1,000 and bumped the metric prefix from mega to giga, and now we have a number which is with an appropriate size. Okay, not too many zeros on the left and not too many zeros on the right. Okay, so did we answer the question? How big is the estimate how big the library is if the books are encoded in ASCII, and the answer is 29.25 gigabytes. Okay. All right, so let's do this again, but now let's assume that we're using PDF. And remember that chart I gave you right at the end of the last lecture? I gave you a chart where I said one PDF page is about 100 kilobytes, okay? Admittedly, that's on the big side, okay? It's a little hard to explain PDF, but there's like you could be small. It could be the amount of information in one page could be small or could be very big. It just depends on how many like complicated symbols there are. Now, I got that estimate using some physics textbooks, and that might be why I might have overestimated a bit, because if you ever take a look at a physics textbook, there are a lot of images in there. There are lots of like, symbols like the integration symbol, differentiation, all these wonderful math symbols that come out of calculus, okay? And so there's a lot of information in a page, and that's why I came up with roughly a 100. But it wouldn't be surprising if you had like just a plain old text, like like something like a novel, and it might be as low as 10 kilobytes per page, but we'll use the 100. Okay, so the number of pages in the library, well, that's the same as in the previous problem. Okay, we have 65,000 books. Each book is on average 300 pages for a total of 19 million plus pages. Okay, now each page, because this is PDF, is 100 kilobytes. Okay, for PDF, and so now if we multiply this out, we're going to get that number there. Okay, and let me put some commas in there so you can see what's going on there and there and there. Okay, and once again, that number is way too big. Okay, so we start off with that. So it's in the billions, so that's like 1,950,000,000 kilobytes. Divide by 1,000, so you basically remove 3 zeros and bump from kilo to the next one up, which is mega. And so now we're at 1,950,000 megabytes, still too big. Divide by 1,000 and bump up again. So now we're at 1,950 gigabytes. Okay, still too big. Divide by 1,000. And now we're not taking off zeros. We're just moving the decimal 3 to the right. 1, 2, 3. So where the comma is there, it gets a decimal. And so now we're at 1.95. And we go from giga to the next one up, which is terabytes. Okay, and so the answer is 1.5 terabytes. So if your library were encoded with these high quality PDFs, then that the entire library, that's 65,000 books, would basically eat up about 1.95 terabytes of data. Okay, now we're going to do a lot more problems like this. This is enough for this point. I got to teach you some more stuff before we can do more complicated word problems. But you'll see later that 1.95 terabytes, 2 terabytes, that's the size of a typical hard drive today. Okay, and so this gives you an idea of just how much information you can store, you can save in a computer. Okay, you could save an entire library of 65,000 books, and there's no way in a lifetime you could read 65,000 books. Okay, even if you read a book a day, you'd only get, you'd only do 365. That means, it would take you 3 years to do 1,000. Okay, and you're not going to live. You're not going to be able to sustain that for very long, and so that's 3 years to get through 1,000 books. Okay, and so if you live to 100, that would only be what would it be for 100? Well, let's say 90. 90 divided by 3 would be 30. So you'd only get up to like 30,000 books, which is a lot. Okay. Okay. Anyhow, so computers can store a lot of information. All right. There you go. That's those are the types of problems that you can do up to this point. All right. Bye bye.